Hello everyone. Once again welcome to my YouTube channel Physics with Dr. Sanjay Bhargav. In this lecture we are going to study about motion in one dimension or motion in a straight line. In this video we'll discuss about the basic concepts of distance, displacement, speed, velocity, difference between distance and displacement, difference between speed and velocity. We will also define average and instantaneous speed, average and instantaneous velocities. We will also discuss about various distance time graphs, displacement time graphs, velocity time graph and the speed time graph. So in this chapter we will begin with defining certain important words. The first word that we pick up is motion. Motion is the change in position of an object with respect to time. So if the position of an object changes with respect to time, then we can say object is in the state of motion. Another word we come across here is mechanics. The branch of physics which deals with the state of rest and the state of motion of objects is called mechanics. So mechanics includes a study of objects at rest and the study of objects in motion. So mechanics can always be studied under two different headings. One would be called as statics, other would be called as dynamics. The branch of mechanics in which we study about the objects at rest is called statics. Now, in static, an important word is state of rest. An object is said to be in the state of rest if its position does not change with respect to time or its surroundings. So how do we define the state of rest? State of rest is defined whenever the position of an object does not change either with respect to time or with respect to surroundings. The next part is the dynamics. How do we define dynamics? Dynamics we define as the branch of mechanics which deals with a study of objects in motion is called dynamics. The study of dynamics is then further classified into kinematics and proper dynamics. Now let us define what is kinematics. It deals with the study of motion of particles without taking into account the cause of a motion. Kinematic requires distance, displacement, speed, velocity, acceleration and time for its study. Dynamics proper, it deals with the study of motion of particles taking into account the cause of a motion. So in kinematics, we do not discuss about what is the cause of motion. In dynamics, we study motion by taking into account what would be the cause of motion. The physical quantities like force, momentum, work, power and energy are required to study dynamics. Another word that we require here is called the frame of reference. The body relative to which a given mechanical motion is being considered is called a reference body. A coordinate frame or a system which is attached to the reference body is called the frame of reference. The combination of this reference body and the coordinate system is together called as frame of reference. So frame of reference, that means something with respect to which we describe motion. Remember, rest and motion are always relative, because for an observer standing on the platform, a person sitting in a moving train appears to be in the state of motion. So if the observer is supposed to be standing on the platform and he watches a person sitting inside a moving train, then the person appears to be in the state of motion. For an observer in the train, the same passenger appears to be at rest. So rest and motion are relative. For certain observers, it would appear the object which appears to be in the state of motion could be at rest in terms of another observer. So the basic question is, where from are we observing the happening or the event? In mechanics, we will be talking about point object. A small piece of matter with no linear dimensions but only position is called a particle. An object is said to be a point object if the distance under consideration are very large as compared to the size of the object. Right? So how do we treat an object to be a point object? Whenever the size of the object is very, very small as compared to the distances under consideration, then it would be treated as a point object. Motion in 1, 2 and 3 dimensions. The position of a point in space is described in terms of the coordinates x, y and z. Remember, in the Cartesian coordinate system, in a two-dimensional plane, the position of a point is described by two coordinates like x and y and z, or z and x. In 3 dimension, it is described by the coordinates x, y and z. On the basis of this, we would be classifying the motion as 1-dimensional, 2-dimensional and 3-dimensional. A motion is said to be 1-dimensional if only one of the coordinate changes with respect to the time. That means either the x coordinate changes or the y coordinate changes or the z coordinate changes. So remember, if one coordinate changes with respect to time, the motion is said to be 1-dimensional. The motion of an object along a straight line is called rectilinear motion. Example, train running on a straight railway track, bus moving on a straight level road. All these motions are taken to be as 1-dimensional motion. A motion is said to be 2-dimensional if coordinates, that means two coordinates, change with respect to time. Then the body is said to be in the state of 2-dimensional motion. In this case, the body would be moving in a plane. Example, motion of a striker on a carom board. That is purely 2-dimensional motion because the carom striker is moving in a plane. Similarly, a motion is said to be 3-dimensional if 3 coordinates change with respect to time. For example, object moving in a space, motion of a kite in the sky, like motion of a fly in space, that is also called as 3-dimensional motion. We can picturize the 3 motions graphically like this. Like if an object starts from point O, after some time it reaches point 1 after covering a distance x1. Similarly, after some time it reaches at point P2, whose position is described by the distance x2 along x-axis. Since the motion is along a single direction x-axis, only the x coordinate is changing, we call such a motion to be 1-dimensional motion. When it comes to 2-dimensional motion, here we consider the motion of an object in a plane. We have the plane xy plane. The object is supposed to be moving from point P1 to point P2. Point P1 described by the 2 coordinates x1, y1. P2 to be described by the 2 coordinates x2, y2. I can drop a perpendicular from point P1 and P2 on the x-axis, which would provide me the distances y1 and y2. Similarly, on the horizontal axis, we can mark the distance x1 and x2. Such a motion in which 2 coordinates are changing with respect to time would be called as 2-dimensional motion. Here we have 3-dimensional motion x, y and z. We again are moving from a point P1 to P2. P1 is being described by x1, y1 and z1. P2 is being described by the coordinates x2, y2 and z2. We can drop the perpendiculars to mark the 3 distances as in the figure. All the distances here, this would be x1, x2, this would be y1, y2 and these distances would be z1 and z2. since three coordinates are changing simultaneously with respect to time, the motion is said to be three-dimensional motion. So in physics we have one-dimensional motion, two-dimensional motion and three-dimensional motion. Motion in which only one coordinate changes with time, one-dimensional. Two coordinates change with time, two-dimensional. And three coordinates changing with time would be three-dimensional. Now let us study position time graph for a stationary particle. A stationary particle means a particle is said to be in the state of rest if its position does not change with respect to time. So on this axis we are plotting position. On the x-axis we are plotting time. The position at the time t1 is x0, at the time t2 is also x0. Since the position is not changing, it is said to be the stationary state of the particle. The position time graph for a stationary particle is a straight line parallel to the time axis. So we can make a position time graph for the stationary state of a particle. Now let us discuss two important physical quantities, distance and displacement. Distance. The total length of the actual path traveled by a body between the initial and final position is called distance. Distance is a scalar quantity with SI unit meter and the dimensions are m0, L1, t0. So actual length of the path traveled by the particle would always be the distance. It's a pure scalar quantities with SI unit meter and dimension m0, L1, t0. The distance never decreases with the time. The distance traveled is always positive. The distance depends on the length of the actual path, so it can have different values between same initial and final points, moving through different paths. Right? So you can have variable distances traveled between same two identical points like A to B, since object would be traveling along different paths. Now let us come to the second quantity under consideration, and that is displacement. The shortest distance between initial and final position is called displacement. Displacement is a vector quantity with SI unit meter and dimension m0, L1, t0. So distance was supposed to be scalar, displacement is supposed to be a vector quantity having the same dimension, having the same unit. Displacement between 2 points always has a single unique value because it is the shortest distance between initial and final positions. It cannot have variable values. Displacement may increase with respect to time or also decrease with respect to time. And displacement may be positive, negative or zero. Difference between distance and displacement. For a moving particle, distance never decreases with the time, while displacement decreases when the particle moves towards the initial point. Like from A to B, here I am moving in this direction. When I move from B to A, then the displacement is decreasing with respect to time. The least value of distance covered by a moving particle is equal to magnitude of its displacement. So we can say the least value of distance covered by a moving particle is equal to magnitude of its displacement. So distance traveled would always be either greater or equal to magnitude of displacement. Distance and displacement are equal only if the motion is along a straight line, and that too only in one direction. For a moving particle, distance is never zero or negative, but displacement can be zero. When a particle comes back to its initial position, its displacement is zero. Like moving from point A to B, and then returning back from B to A makes the displacement 0. But the distance traveled is twice the distance between A and B. The displacement is known only if its initial and final positions are known. That is, displacement is independent of path and distance is path dependent. So I think this discussion would help you in understanding the difference between distance and displacement. Now we come to two important quantities of one-dimensional motion, that is speed and velocity. Speed. The rate of change of distance with respect to time in any direction is called speed. It is numerically equal to the ratio of total distance traveled to the total time taken. Speed is equal to total distance traveled upon total time taken. Similarly, I like to define velocity. So when it comes to velocity, the rate of change of displacement with respect to time is called velocity. It is numerically equal to the ratio of displacement and time. So velocity is equal to the ratio of displacement and the time taken. Now, what are the differences between speed and velocity? Let us pick up. In case of speed, the direction of motion is not fixed, but velocity has a specified direction. The speed in a specific direction is called velocity. So speed is supposed to be a scalar quantity, velocity is a vector. The magnitude of velocity is called speed. So speed would be equal to magnitude of velocity. Velocity can be positive or negative, but the speed is either positive or 0. Mathematically, speed is equal to magnitude of the velocity and is greater than equal to 0. Now we come across a word called uniform motion. The motion of an object is said to be uniform if it covers equal displacements in equal intervals of time, however small these intervals may be. In uniform motion, its position coordinate is a linear function of time. X, position coordinate of object at the time t, x dash, position coordinate of the object at a new time t dash. Displacement of the object in time t to t dash is x dash minus x. So how do we define velocity in uniform motion? Displacement upon the time interval. Displacement is x dash minus x upon time interval t dash minus t. How do we graphically represent uniform motion? So we like to have graphical representation of a uniform motion. Uniform motion is represented in two ways: velocity time graph and the position time graph. Now let us first pick up is velocity time graph. For a particle moving with uniform velocity v towards right or upwards, the vt graph is shown here. Now let us look at the vt graph. On the y-axis we are plotting velocity, right? On this axis we are plotting velocity. On this axis we have taken time. At the point velocity v, the magnitude is not changing. For particle moving with a uniform velocity v towards left or downward, the vt graph is a dotted line below the time axis, and this represents velocity time graph of a particle moving either in upward direction or towards right. The velocity time graph helps us to calculate the distance covered by the particle from time t to t dash. It can always be calculated as the area under the curve ABCD. So area ABCD is equal to BC into AB, that is V into t dash minus t, and that is distance covered in the time interval t dash minus t. The area enclosed by the velocity time graph and the time axis gives the distance covered in the time interval t dash minus t. So by using velocity time graph, we can calculate the distance that would be traveled in a given time interval. The second graph that we want to discuss is the position time graph, that is xt graph. In uniform motion, the position coordinate x is a linear function of time. The graph between x and t is a straight line. Though xt graph is a straight line inclined to the time axis, it can have different orientations depending on the nature, that is positive or negative, of x0 and v. Now let us take this. This is position time graph. On this axis we are plotting position, and on this axis we are plotting time. When the time t is equal to 0, the position x is x0. So we begin from x0. Both x0 and v are positive. Now at the initial time t, the position is at A. At the time t dash, the position is at C. The angle made here is alpha with respect to horizontal. Now what is the information that we are obtaining from the graph? The position time graph enables us to determine the velocity of the particle. The slope of the position time graph for uniform motion is equal to the velocity of motion. So once I calculate the slope of this graph, a straight line, that slope provides me a measure of velocity of uniform motion. So velocity is equal to x dash minus x upon t dash minus t is equal to bc upon ab is equal to tangent alpha, which is nothing but slope of the position time graph. Hope this video is helping all of you in improving the concepts of one-dimensional motion. If the video is useful, I request you to subscribe my channel, like my videos and comment on my videos to let me know how do you feel and understand with respect to the use of these videos. Now we are moving to study about different formulas related with uniform motion. Let us consider a particle moving with uniform velocity v. Let x0 be the position of the particle at time t is equal to 0, x be the position of the particle at the time t is equal to t. So v would be equal to x minus x0 upon t minus 0. Rearranging, I can write x would be equal to x0 plus vt. Let this be equation number 1. What does this equation provide? It tells me what would be the position of an object moving with uniform velocity v after time t. Now if x dash is the position coordinate at the other time t dash such that t dash is greater than t, then x dash would be equal to x0 plus vt dash. So x dash minus x would be equal to v into t dash minus t, or x dash would be equal to x plus v into t minus t dash. Equation number 1 and 3 are the two formulas for uniform motion, right? For non-uniform motion, let us first describe what is non-uniform motion. The motion of an object is said to be non-uniform if it covers equal distances in unequal intervals of time, or unequal distance in equal intervals of time, or if the direction of motion is reversed. For non-uniform motion, we cannot say any definite things about velocity or speed. If we want to study motion in some definite segment of path, we need to introduce the idea of average velocity and average speed of the motion. So in non-uniform motion, what is happening? The object would be called to have a state of non-uniform motion if it covers equal distances in unequal intervals of time, or unequal distance in equal intervals of time, or if the direction of motion is reversed. For non-uniform motion, we cannot have definite values of velocity or speed. If we want to study motion in some definite interval, then we need to introduce the concept of average velocity and average acceleration. Now we like to define average velocity and average speed. We have already shown why do we require the concept of average velocity and average speed. We require both of them just to study a specific part of non-uniform motion. How do we define average velocity? The average velocity is defined as the ratio of total displacement to total time interval in which the displacement takes place. We begin the motion from point O at the time t1, we are at the point p1 by covering a distance x1. Similarly, after some time t2, we are at the point p2 and we describe a distance x2. If I want to study somewhat a motion between point p1 and p2, then x2 minus x1 is equal to delta x. Here delta x is called the displacement from the point p1 to p2. And similarly, t2 minus t1 is called delta t, that is the time interval. How do we define average velocity? Average velocity would be defined as delta x upon delta t. Average velocity is a vector quantity. So we are talking about an interval now, interval of time t2 minus t1, in which the displacement is delta x, that is x2 minus x1. Similarly, we can talk about average speed. The average speed is defined as the ratio of total distance traveled to the corresponding time interval. So total displacement upon total time, average velocity. Ratio of total distance upon total time, that would be called as average speed. Now, what is the difference between average speed and average velocity? Average speed is a scalar, while average velocity is a vector. Average speed is always positive, while average velocity can be positive or negative depending on the sign of displacement. So what is the sign of average velocity? It has the same sign as that of average displacement. And average velocity could be 0 when the displacement is 0. For a given time interval, average speed can have many values depending on the path between initial and final positions, while average velocity will always have a unique value, because displacement has a unique value. In speed, distance can be different depending on the nature of the path. Generally, average speed is not equal to the magnitude of average velocity. They are equal only in rectilinear motion, that is uniform motion in a straight line. Normally, average speed would be greater than or equal to magnitude of average velocity. Average speed is equal to magnitude of average velocity in case of motion along a straight line without change of direction. Then we require another concept of instantaneous velocity and instantaneous speed. How do we define instantaneous velocity? The average velocity tells us how fast an object is moving over a given time interval, but it does not tell us how fast it moves at different instants of time during that interval. For this, we require the concept of instantaneous velocity. Instantaneous velocity is the velocity of an object at a given instant of time or at a particular point on its path. So, instantaneous velocity is a specific velocity at a given time or at a given position. Instantaneous velocity is equal to the instantaneous rate of change of position with respect to time, and is the limit of average velocity delta x by delta t as the time interval delta t approaches 0. So let us go to the mathematical definition of instantaneous velocity. Instantaneous velocity, limit delta t tending to 0, then average velocity would convert to instantaneous velocity. Limit delta t tending to 0, delta x by delta t can be written as dx by dt. If motion is uniform, both average and instantaneous velocities are equal. If the motion is non-uniform, instantaneous velocity is different at different instants of time. Then we have instantaneous speed. The absolute magnitude of instantaneous velocity without reference to its direction is called the instantaneous speed. So instantaneous speed is magnitude of instantaneous velocity without a specific direction. Difference between instantaneous speed and velocity. Velocity is a vector while speed is a scalar. If velocity is constant, speed is also constant. But the converse is not true. If the speed is constant, velocity may change due to change of direction. So velocity is constant, that means specific direction, then speed would also be constant. But the converse is not true. Very important thing to be noticed here is, if the speed is constant, velocity may change, and it may change due to change of direction. So velocity can change either by the change of magnitude or by the change of direction, since velocity is a vector. Velocity may be positive or negative as it's a vector, but speed can never be negative as it's the magnitude of the velocity. Graphical determination of average and instantaneous speed velocities from position time graph. Average velocity. The average velocity between 2 points is equal to the slope of a straight line joining these 2 points on a position time graph. So we require average velocity between 2 points A and B. So we join them with the help of a straight line. The slope of the straight line would provide me the average velocity. The slope of that straight line AB is BC upon AC. BC is delta x and AC is delta t. So average velocity would be given by delta x by delta t. So what is average velocity? It is nothing but the slope of a straight line AB drawn on a position time graph. Instantaneous velocity. The instantaneous velocity at a point is equal to the slope of the tangent to the position time graph at that point. When the point B approaches A, then delta t is tending to 0. In this condition, the straight line AB would become a tangent to the graph at A. Just look in the figure. If this point B approaches A, that means it becomes here. Then what will happen? This would work like a tangent, and the slope of this tangent would give me this instantaneous velocity at point A. So here, limit delta t tending to 0, delta x by delta t would be equal to limit delta t tending to 0 slope of a straight line AB, and it would convert to the slope of tangent at point A. Limit delta t tending to 0, delta x by delta t is equal to dx by dt is v, that is instantaneous velocity at A. So v would be equal to slope of the tangent at A. That is how we calculate instantaneous velocity. Now let us find out determination of average speed under different situations. Let us pick up a case first. A body covers different distances s1 and s2 with different speeds v1 and v2. Then we are asked to calculate what would be the average speed. It would be total distance covered upon the total time taken. In the time t1, we can calculate it would be s1 upon v1. Similarly, time t2 would be s2 upon v2. Just substitute here. Then average velocity would be given by s1 upon s2 upon total time, that is s1 by v1 plus s2 by v2. Under the special condition, let S1 and S2 be equal to S. Then average velocity would be given by 2S upon S into 1 upon V1 plus 1 upon V2. S cancels here. So we get 2 V1 V2 upon V1 plus V2. A very important relation for us. If an object travels equal distances with equal speeds, then average speed is equal to the harmonic mean of the individual speeds. So if an object, if a body travels through equal distances in equal intervals of time, then average speed would be given by the harmonic mean of the individual speeds. Now we pick up second case, and here the body moves with different speeds V1 and V2 for different times T1 and T2. Now the average speed would be given by total distance upon total time. So we are having, for time T1 it was moving with a speed V1, for the time T2 it was moving with a speed V2. So the distance S1 is V1 T1, distance S2 is V2 T2. So total distance upon total time. Here if the times are equal, there the distance intervals were equal, here the time intervals are equal, then average velocity would be given by T into V1 plus V2 upon 2T. Time cancels here, so average speed would be given by V1 plus V2 upon 2. So if the time intervals are equal, then the average speed would be equal to the arithmetic mean of the individual speeds. Now we pick up various type of graphs. Sometimes we are asked to analyze the nature of motion by looking at the graph. So we have different types of either distance time graph, we may have displacement time graph, we may have the speed time graph, we may have the velocity time graph. So on the basis of these graphs, we need to draw some information from the graphs just by looking at the shape of the graph. First, we pick up distance time graph. Let us pick up the first graph. What does it say? On the y-axis, we are plotting the distance. On the x-axis, we are plotting the time. This represents a distance time graph for an object at rest. The slope AB is 0. So the speed of the object is also 0. So what does this graph describe? It describes the stationary state of an object. Similarly, we have a graph, straight line graph, which is a straight line OA passing through the origin O. This is the distance time graph for an object moving with the uniform speed, and it is a straight line inclined to the time axis. The graph passes through the origin O, so distance traveled at the time t is also 0. Then we have another two graphs of distance and time, one sloping upward, another sloping or bending downwards. In this case, what is happening? The slope of the graph is increasing with the time, so represents accelerated, speeding up motion. Here the slope is increasing, that means the speed is increasing. Here in this case the slope is decreasing, and therefore it represents decelerated motion, a motion in which the speed decreases with respect to time. Now we want to discuss some different type of displacement time graph. On y-axis we have displacement, on x-axis we have time. This is again a graph for a stationary object. The displacement time graph is a straight line parallel to the time axis. The zero slope of the line, straight line, gives me zero velocity. Here in this case the displacement time graph is a straight line OA inclined to the time axis. It has a unique slope. It represents a case of constant velocity and zero acceleration. So every time a different information can always be obtained from a given shape of the graph. Here we have two displacement time graphs, one sloping or curvature increasing upward, another bending downwards. In my first graph, what do I observe? We observe that slope of the graph is increasing with the time. So graph represents an increasing velocity or an accelerated motion. For constant acceleration, the displacement time graph is a parabola bending upwards. Here, decreasing displacements are taking place in equal intervals of time. So, displacement time graph represents a decreasing velocity or deceleration. For uniform deceleration, the displacement time graph is a parabola bending downwards. In this case, it is downwards. Another displacement time graph, the displacement is increasing. In this case, just look here, the slope is decreasing. So we say displacement is decreasing uniformly with time and becomes zero at some time. Displacement time graph has a negative slope and represents uniform negative velocity. What does it show? It shows a body returning back to its original position with uniform velocity. In this second figure, what do we observe? We find that displacement of the body becomes negative after a time t. After time t here, the displacement of the body becomes negative and then increases in magnitude with time t. It indicates a body returning from position A, moving past original position B and then moves towards C with a uniform velocity. So once again, different type of information obtained from different graphs. Let us have a look at some velocity time graph. On this axis we have velocity, on this axis we have time. What does the VT graph show? The VT graph shows a body moving with uniform velocity, and that comes out to be a straight line. It's parallel to x-axis. The slope is zero. That means the body has zero acceleration. It's a case of uniform motion. Here we have a VT graph for a body moving or starting from rest with uniform acceleration, and that comes out to be a straight line OA inclined to the time axis passing through the origin. More is the slope of the VT curve, more would be the acceleration. Now we have two graphs once again here. When I say this one, it says at the time t is equal to 0, body has some initial velocity u. The straight line VT graph does not pass through the origin O here. The body has an initial velocity u is equal to OA and then it moves with uniform constant acceleration because the slope remains the same. Here in this case the graph shows larger changes in velocity in equal intervals of time. The VT graph is bending upwards, representing increasing acceleration with respect to time. In this case, the graph shows smaller changes in velocity in equal intervals of time. The VT graph bending downwards represents decreasing acceleration. In the graph here, the body starts with initial speed u from the point A. The velocity decreases uniformly with the time, becomes a zero after some time. As theta is greater than pi by 2, the graph has a negative slope. This VT graph represents motion with uniform negative acceleration. So again we have two VT graphs. The first one, the VT graph represents a body projected upward with initial velocity u. Then what happens? The velocity decreases with time, becomes a zero at the time t, and then velocity becomes negative and increases in magnitude, returns to the original position with positive acceleration. In this curve, it's a sine curve. The area between velocity time graph and the time axis gives the displacement. The VT graph shows variable acceleration. We can calculate displacement and distance covered from the graph. Displacement covered would be area of the first loop minus area of the second loop plus area of the third one. And the distance covered would be area of the first, second and the third loops of the graph. Now let us see some different types of speed time graph. In the first case, It represents a speed time graph for a body projected upward. When a body moves, its speed decreases uniformly, which is shown here. Becomes a zero at the highest point. So at the highest point it becomes zero. As the body moves down, the speed increases with the time, and that is what is shown here. Now, it returns with the same speed with which it was thrown, and that is why the height of the two curves is same. Here you can see that height of the curve is same. Now what does this graph show? It represents a speed time graph for a ball dropped on ground from some height h. As the ball falls, its speed increases. As it bounces back, its speed decreases uniformly and becomes a zero at the highest point. So these are the two types of motion, one in which the body was projected upward and another a body was dropped from a height h. Hope all of you might have enjoyed this video and learned some basic concepts of one-dimensional motion. If you like the video, we request you to subscribe the channel, make some comments on the video, like the video. And another note here, the remaining one-dimensional motion will follow in part 2. Thank you all.